learning in cat-mouse strategy, a study contrasting Q-learning with Dijkstra's algorithm aimed at evaluating AI performance in dynamic setups, with implications for fields like autonomous navigation. I created a JavaScript-based game to pit a Dijkstra's algorithm-driven cat against a mouse. Through Q-learning, I trained successive generations of cats and mice, each learning from the previous to refine evasion and pursuit tactics. The goal of each cat is to catch or prevent the mouse from leaving the maze, while the goal of the mouse is to avoid getting caught and to escape safely. Just to do a quick overview of Dijkstra's algorithm. Given the 8x8 graph, a length of 1 is encoded into each path tile, while a length of 64 is encoded into each wall. The cat is then able to calculate the shortest path towards the mouse, as seen by the highlighted coordinates. The corresponding rows and columns in which the cat has to take is determined by the algorithm. Now to move on, the first training process, which involves training the blank slate mouse against Dijkstra's cat, I would like to start off by talking about the MDP. The states for this training process include the possible mouse's locations, which exclude all walls. We therefore have 45 blank tiles in this map. We also have 4 possible directions the cat can be coming from, which is found by the path the cat is taking towards the mouse, and we take into account the distance from the cat to the mouse. The rightmost table shows the maximum shortest distance from each coordinate to every other coordinate. For example, if we take a look at the coordinate row 7, column 6, in which the mouse is in, and revert to the previous slide, when we scan across this array, the maximum value on a valid path is 15, and thus the value here in row 7 and column 6 is 15. If we take the maximum value in this entire table right now, it is 15, which is why 15 is known as the maximum distance the cat can be from the mouse. However, this is an upper bound. If we create the state space to account for the fact that in some coordinates, the maximum distance from the cat to the mouse can be less, and also the fact that the cat may not always be able to come from all 4 directions, then we'd reduce our state space significantly. There are 4 possible actions the mouse can take. If the mouse takes an action against the wall, it will remain in the same spot. In terms of the rewards, since the mouse is working against Dijkstra's algorithm, we know that the distance between the cat and mouse cannot increase. It will either stay the same or decrease. Because of this, we will always offer a positive reward if the mouse maintains its distance from the cat. We take the maximum distance value determined in the previous slide and use it as a baseline value for our reward. When the mouse maintains its distance from the cat, it could either be getting closer to the exit or not. When it's staying away from the cat and getting closer to the exit, we give it a reward of the maximum distance. Otherwise, we will give it half of that. Now, the only acceptable time for which the mouse should travel towards the cat is if it is also traveling towards the exit, and we know the mouse will reach the exit before the cat reaches it. An example of this is shown on the top right image. Otherwise, for all other cases, the mouse will be traveling or getting closer to the cat at the expense of its life. When this happens, we penalize it by applying a negative reward, which is defined as the negative value of the maximum distance subtracted by the distance between the cat and mouse. This ensures that the penalty increases when the cat is closer to the mouse. An example of this is shown on the bottom right image, where the distance between the cat and mouse is 2, and we therefore end up with a penalty of negative 13, assuming the mouse did not maintain its distance from the cat. The transition probabilities, which typically define the likelihood of moving from one state to another in an MDP, are implicit within the environment's dynamics rather than being explicitly known or calculated. The learning process of the mouse employs the epsilon greedy strategy, a crucial element for balancing exploration and exploitation. We start off with an epsilon value of 0.9 and an epsilon decay rate of 0.9998666, which is calculated with a goal of training for about 30,000 episodes. Each episode is terminated when either the mouse is caught or escapes. Regarding the Q-learning algorithm, we use the Bellman equation to update the Q table. The values chosen for the learning rate is 0.95. The discount factor is 0.95. Now to explain the Q-learning algorithm, I'm going to run through a quick example. Let's say we already initialized our Q table and it has been updated many times. Our mouse is in the current state row 1, column 0. The cat is coming from up and it is a distance of 4 away. To choose an action, we would go to the states and the corresponding states in the Q table and find the action with the highest Q value. In this hypothetical example, it would be up. After moving up, the environment will respond. In this case, the cat is the environment and it responds by moving left. The new state the mouse is in will therefore be row 0, column 0. The cat is coming from the right and it is a distance of 2 away. The given reward in this scenario is 15, since the mouse is closer to the exit than the cat is. To evaluate the new Q value at the state row 1, column 0, up, and distance of 4, while taking action up, we take the old value for this action, which is 5, and plug it into the equation. Another value we need is the maximum Q value of the transition destination state. This is the value of 5 as seen in the Q table at state 00R2. After calculating, we replace the Q value in state 10U4 with the new value of 19.01. The evaluation of the result was done every 100 episodes. The evaluation will then run 200 evaluating episodes in which it measures how the mouse is doing. There are two important requirements when evaluating the performance and running the evaluation episodes. The first is freezing the Q table so this does not affect our actual training process. The second is having the opposing agent take the most optimal action so that we may understand how well our learning agent is doing against a true environment. In this case, the Dijkstra's cat will do so anyways, but in our future training sessions, this is important to remember. The success rate across the training process is shown in the graph. Success in this case is defined when the mouse reaches the exit. In addition to success rate, the average path length taken before the mouse escaped the maze can be seen on the left. In the initial stages, the path length is short, indicating that the mouse already spawned near the exit, which explains why it was able to reach it even with a less developed Q table. Another graph shown to the right is the average path length taken before getting caught. As the training progresses, the mouse is not caught at all. Towards the end of the training process of Dijkstra's cat versus the Generation 1 Q-learning mouse, the problem of deadlocks arises. A sequence of actions performed by the cat and mouse is shown. The red numbers display the length of the path from cat to mouse. Assuming it is the mouse's turn to perform an action, on the leftmost image, it performs the action down, as shown in the second image. The cat responds by moving down, as well in the third image. In the fourth image, the mouse responds by moving up. The cat will respond by moving up again. This result is in a never-ending cycle. In order to escape a deadlock, a function was written to check for repeating states. The chances of being in the exact same state before is not high, unless we are in a deadlock. Therefore, whenever a repeating state is detected, the mouse will take the second highest value action rather than the highest. Moving on to the second training scenario, we now have two reinforcement learning agents where a blank slate cat is learning from the already well-trained mouse. The state space now takes into account all possible positions to both the cat and mouse exist in. One of the reasons for this is because we can no longer rely on the fact that we know the direction which the other agent is coming from, as it is not as simple or deterministic as Dijkstra's algorithm. The rewards are constructed to highlight the importance of blocking the mouse from leaving the exit and catching it. When training the cat, we introduce three additional factors into our rewards. Goalkeeping mode. Goalkeeping mode is when the cat is closer to the exit than the mouse is to the exit. The top left image is an example of the cat in goalkeeping mode. Catch-up mode. Catch-up mode is when the mouse is closer to the exit than the cat is to the exit. The top right image is an example of the cat in catch-up mode. Exit difference. This is defined as the distance from the mouse to the exit minus the distance from the cat to the exit. In the bottom image, the distance from the mouse to the exit is 5, while the distance from the cat to the exit is 8. The exit difference is therefore -3. The first two rewards are based on the change of state in goalkeeping or catch-up mode. If one of the reward conditions are met, we no longer consider the conditions or rewards below. Since the cat is always at an advantage in the goalkeeping mode, we penalize it for switching from this and reward it for transitioning into it. The other rewards depend on whether the cat gets closer to the mouse and whether the exit difference changes. The conditions in which the cat gets closer to the mouse are ideally what we want and are highlighted in green. A greater reward is applied for increasing the exit difference, while a lesser one is applied for decreasing it. The orange conditions are when the cat maintains distance from the mouse, and the red conditions are when the cat gets further from the mouse. Training two RL agents against one another is similar to attempting to create a sword that can pierce anything and a shield that can block anything. Training a blank slate cat against a proficient mouse with a complete Q table may limit the cat's learning of certain strategies, such as catching the mouse, if the mouse always evades successfully. On the other hand, training the cat against a mouse that acts randomly is also suboptimal. In this case, the mouse's random moves towards the cat could falsely lead the cat to believe its strategy is effective, which is misleading as the mouse should realistically represent a challenging target for the cat to pursue. In order to combat this problem, we will have the mouse take the less optimal option every once in a while, just enough for the cat to learn how to catch it. We will change the mouse's probability of taking an optimal versus less optimal action as epsilon decays. This promotes exploring in the initial stages, and as the cat becomes greedy, we can pit it against the smarter, less forgiving version of the mouse. In the interest of time, I will not go over the performance of training the other agents, but the approach to training the generation 2 agents are very similar. The results of all the training processes can be found in the paper. Now onto the demo. Here we see how well our mice play. On the left, we have Dijkstra's cat playing against the Generation 1 Q-learning mouse, and on the right, we have the Dijkstra's cat playing against the Generation 2 Q-learning mouse. As you can see, both mice are able to navigate their way out of the maze and avoid getting caught for the majority of the time. Here we see how well our cats play. On the left, we have the Generation 1 Q-learning cat and mouse playing against one another. On the right, we have the Generation 2 Q-learning cat playing against the Generation 1 Q-learning mouse. When evaluating the cat performance here, some additional things I had to do was set up a stalemate counter because of the possibility of the two agents getting stuck going back and forth at some parts in the maze. I also had to introduce some slight randomness into the mouse's actions, such as having it take the second best action every once in a while so that we could actually see the agents interact instead of shuffling back and forth.